Here we go, guys. Okay, we're recording. Welcome to Office Hours today. This will run, of course, the usual time. I apologize if it's noisy behind me. Apparently, my neighbors are doing construction. So, to answer the first question I received in the chat for the graphs, and I will send out an email clarifying this. The graphs are the four graphs mentioned in the actual work. The stapled part, the first four parts of the lab that is due this week. There are four graphs you should be doing. I generated the data for you and provided the graph, and I just provided you the raw data so you could see the data that the graph came from. But as far as BMI goes, the graph is already generated. You do not need to generate that. I just wanted you guys to have the graph and the data available to you. I hope that makes sense. Now, let's fire up PowerPoint. We've got a homework question from chapter 2. Okay. Okay. Yes, your four graphs will come from the four tables of data you collected. Okay, now let's get some blank slides here. PowerPoint works great for this, of course. Now the question that we are having is on the chapter. Let me see if I can open up the text. Should be here. Okay, so the text is there, and the question is about number 36 from chapter 2, 38 as well. Okay, let's see what I can do about that. Chapter 2, question 36. That one. I'm just going to take a quick screenshot of it from my ebook. So we'll start with number 36. So, and then I'll give myself a few slides, and then number 38, I think the question is about as well. Yes. There's that. Okay. Are there any other questions from chapter 2 that we would like to line up for this office hour session?
I wanted to ask you about the quadrants, the S, SP, D, and F. Is that that video you sent from Melissa? It seemed to make the most sense to me.
Okay.
But I did have a question about electron subshells compared to orbitals, I guess it is.
Mhm.
because the subshells and the orbitals are two different things, and I think that I'm confusing the two.
Easy to do, yes. Not a problem. We can definitely go through that. Which one is the highest priority for you? The questions you asked from the homework or that conceptual one?
Probably the questions from the homework.
Okay. I just want to make sure that I prioritize your questions to make sure that I have enough time to do the best I can to cover.
Right.
Yeah. Okay. So let's see. Trying to make sure that I answer everyone's questions, of course, and I will do my best to make sure I get to everyone. Let's see here. Sharing the screen. Okay, so here's question. This is number 2, chapter 2, question 36. Hopefully you guys can now see my screen. There we are. Okay. All right, so what mass in grams of 6.022 times 10 to the 23rd oxygen atoms of, okay, yeah, so what is the mass in grams of this number, so 6.022 times 10 to the 23rd oxygen atoms with a mass of 16.00 AMU? So the first thing we can do is find the mass of one oxygen atom. And the long way of doing this, which is the way technically that I believe the book, I believe this is the easiest way to do it. So we're going to use 1.67 times 10 to the minus, what does the book use? I always forget. The mass of a proton and the mass of a neutron is, let's see, neutron, that does not help. Give it to me in actual quantities. Symbols is useless. There we go. Okay. I don't need the mass in AMU. I need it in grams. I'll make sure. There we go. Okay, 1 point, yes. Times 10 to the minus 24. So 1.672 versus 1.674. So we're just going to say that the mass of a proton or a neutron, we're just going to approximate it to 1.67 times 10 to the minus 24 grams for the sake of ease. Now, oxygen has Z, the atomic number, equal to 16. And when we look at our periodic table, the atomic mass listed, let's see, the periodic table right behind me, there it is. The atomic mass is, oh wait, no, sorry, the atomic mass, yeah, of course, that's why my brain's going, no, that's wrong, that's wrong, that's wrong. It's been a long day already, yes. So the atomic number of oxygen is 8. The atomic number is 8. The atomic mass is 16. Technically the mass number is equal to 16. And we know that A is equal to number of neutrons plus number of protons, and we know that the atomic number Z is equal to the number of protons. So what we can do then is say that one atom is equal to 8 protons times 1.67 times 10 to the minus 24 grams plus 8 neutrons times 1. Because this is per proton, and 1.67 times 10 to the minus 24 grams per neutron. And so you can see if you do that, really what it comes down to is 16 times. You guys following me so far?
Yeah.
Okay. 1.67. I'm always apparently using a different calculator than one I remember using before. 1.67 times 10 to the minus 24. When I do that, of course, I get something on the order of 2.672 times 10 to the minus 23 grams per oxygen atom. So finally, we can go mass of 6.0, darn it, sorry. There we are. 6.022 times 10 to the 23rd oxygen atoms. It's going to be equal to, of course, that number, 6.022 times 10 to the 23rd, multiplied by 2.672 times 10 to the minus 23rd grams per oxygen atom. This is not going to work out the way I want it to. That's the problem. Comes out to, actually, no, it does kind of work out the way I want it to. Yes, it does. It comes out to, what is the mass? Yes, exactly. It is 16.09 grams. Yes, that is exactly the answer I should get. 16.09 grams. There we are. Now, this chapter doesn't go into why this is the mass you should expect to get from that number. But I will tell you, does anyone need more time with this slide to begin with?
No.
Okay. Let me check the chat. Because of course I know I haven't checked the chat. There's no question. There's nothing in the chat at the moment. Okay. Now, do you guys follow what I've done so far?
I guess why is my question. Why?
Okay.
Why you did that?
Okay. So, basically, what I have done is I'm told you have. So what the question did was the question gave me a quantity or number of atoms, right? And then asked for the mass of that quantity of atoms, if you will. That's exactly what it did, right? So what I needed to do was create somehow a conversion between number of atoms and mass. I needed to be able to go back and forth between particles of the element and the total mass of that quantity of atoms. Does that make sense so far?
Yes.
Okay. So I had to do that because the question is literally saying, what's the mass of X number of what's the mass of X amount of particles? And the only way to do that is if I actually have a conversion factor. And I apologize to the people who are getting stuck in the waiting room. Apparently,
Kill him. Shh.
so what we're looking at, yeah, is this is a conversion. And so therefore I had to create that conversion factor. And so what I did was, the first thing I did on the previous slide was, I went 1, find the mass of 1 atom, which I did using the mass of the subatomic particles in the nucleus. Because that's the major contributor of mass for an atom. The mass coming from electrons is so negligible. And I did do a calculation a couple of weeks ago showing that, or last week, I think even, showing that if you calculate using the mass of the electrons, it's so negligible that with regard to significant figures, it actually is insignificant to incorporate the mass of the electrons. And so with that in mind, then we ignore the electrons as far as mass of an atom goes, but we find the mass of a single atom utilizing all the subatomic particles. And that's what I did here on the previous slide. I went, okay, 1 atom has 8 protons, 8 neutrons. Let's multiply each mass of those together and sum that together to get the mass of a single atom. Then take the number of atoms. So this right here, 6.022 times 10 to the 23rd, has units of oxygen atoms, and multiplied it by 2.672 times 10 to the minus 23rd grams per oxygen atom. And doing that multiplication, you can see units of oxygen atoms will cancel here and there, leaving behind mass of oxygen. And then therefore I get grams of oxygen as 16.09 grams of oxygen. How's that?
Sounds good.
Okay, so making more sense, I hope.
Yes, a little bit. Is that I'm gonna try to. I took screenshots. Is that I'm gonna try to fumble my way through it.
Okay, no problem. This will get easier when we get to the topic of the mole, and I'll give you guys a spoiler if you're okay with me flipping through these slides now. Okay, still nothing in the chat. Okay, so next slide is this one. So yeah, found the mass of 1 atom using the mass of the subatomic particles in the nucleus, and then 2, used that mass of 1 atom to find total mass of 6.022 times 10 to the 23rd atoms of that element. And what it turns out is that if you have 6.022 times 10 to the 23rd atoms of any element, that will have exactly the mass of that element. The grams will be equal to the number of AMU found in the nucleus. And that's a big deal. This is something we will go over in another chapter, so I don't want to focus on it, but it turns out that we have this thing in chemistry that some of you guys know, some of you have heard, 1 mole, which is equal to 6.022 times 10 to the 23rd anythings per mole of anything. So it can be 6.022 times 10 to the 23rd atoms of oxygen per mole of oxygen. 6.022 times 10 to the 23rd humans per mole of humans, whatever you want to call that unit. So for example, 1 mole of oxygen atoms contains 6.022 times 10 to the 23rd oxygen atoms. Thank you, Avogadro, for predicting this. I think it was actually a Russian scientist who worked this out, but long story, history, etc. And it turns out that for physical mass, that 1 mole of a substance will have grams equal to the AMU of that substance. That's not something you need to know right now. You don't even need to know that, I don't think.
So is that 1.67 times 10 to the minus 23 that you had on the other side? Is that like the standard when we're approaching this type of problem? Is that the I'm sorry, 10 to the minus 24? Is that standard for all of these types of problems? Is that something that we'd use for converting AMUs into grams?
In the short term, yes. In the short term, you would go about calculating the mass of 1 atom. So it would be, you'd find the number of protons and number of neutrons in 1 atom, and then you would use that to get a mass per atom conversion factor in the short term. It will get easier once we can talk about the moles. We won't have to do this calculation forever. This is just to make you guys appreciate essentially the moles, and it also is from the perspective of how to teach chemistry. It is one approach to it, and that's what that's the way I tend to view it, best taught before we actually go through the concept of the mole. Yes, because keep in mind this mass right here, that number right there, this is the mass of 1 neutron or 1 proton.
Yeah.
That makes sense?
Yeah.
Okay. So
I think we should give somebody else a chance to ask a question.
I would agree, and I appreciate you saying so. I'll try to come back to the other question you asked as well. Let's see. Does anyone else have a different question that they would like answered in relationship to a homework problem or the labs?
Yeah, I have a question, Professor.
Certainly.
So on the chart where it says like calculate BMI, it says BMI according to the textbook chart. I tried looking for it. Do you know where it is in the textbook, or should we just like look it up online?
That's a good question. One of the many things that seems to have been an oversight in this lab that I figured they had figured out, but more fool me for not having checked every tiny note.
No worries. It's all over online if you want. It's your choice.
Yes. So could you, if you have already found it, could you email it to me?
Like a version of it.
Absolutely, yes. Because if you happen to have already found it, you'll save me time, and yeah, that is perfectly acceptable as far as I'm concerned to use. Yeah.
All right.
Yeah, if you send that to me, I'll make sure that everyone else gets it, and I can actually take a look at it and make sure that it is the right one to be using.
All right.
Yeah.
All right, perfect. And then I got one more small question for the to find the thickness of aluminum in for that part of the lab. Are we supposed to? I found 3 different I guess, thicknesses for 3 different pieces of aluminum. Are we just supposed to get one number or?
Were they in general pretty close to each other?
Yes.
Okay. The best thing to do, if you really wanted to do it, in my opinion, the way that I would do it, approximating something that would be done in a lab, an
Mhm.
experimental lab, you would actually calculate an average. Now, when it comes to this lab and this class, I'm fine with you guys having done one calculation, but if you want to do the little slight extra step of doing an average, that's awesome. Okay.
All right.
Yeah. It sounds like you're totally on top of it, and yeah, no, you've done beyond the bare minimum of what I was anticipating for this lab. Because when you look at the lab, it just has like space for one answer, and it doesn't even ask for more than one calculation.
Yeah,
So
I wasn't sure, so I did all 3, and I used the analytical because it seemed like the weights were a little bit more precise on those.
it absolutely is. That's why it's called the analytical balance in the first place. I was trying not to say this, but the reason that is called an analytical balance is because it's the balance you use for analysis, and those types of analytical balances with that accuracy, or sorry, that level of precision, or even an additional decimal place, but definitely with the same sorts of doors, are exactly what you'll use over and over again in research labs across the country and around the world.
All right, I appreciate it.
No problem.
I'll try to find the chart that I used. I'll send
Thank
it
you.
over to you right
Thank
now.
you. Thank you. I appreciate that.
Yep. Appreciate it again, Professor.
No problem. You got it. Are there any other questions? If there aren't any other questions, then I will return to David's question. I just want to make sure that someone else does not have a different question pressing aside from chapter 2, number 38.
I have a question.
Certainly.
So for the lab that we turn in on Tuesday, measurements in chemistry,
Yes.
I'm confused on how to label and what numbers to put in for the data, like the table, in order to generate a plot, like a graph.
Okay, so let's see. How can I do this? Okay, I'm going to stop that for a second. And then we are going to look at, so your question is, what data from the lab do you need to use to generate the graphs?
Yes, and I made an account on Office to have Excel, so I was just curious on how to do that. And then also, do we screenshot or take a picture of it when we're finished with it to show you the results?
So ideally, you would be able to save the 4 graphs as files that you could print out, or that you could put into a document that you've created, or submit even with your homework. Ideally, you'd be able to save them either as some sort of image or PDF. Ideally. Are you using your own personal email account for this Office account, or are you using your community college account?
It's personal.
Okay. Because you should, if you log into Microsoft Office with your community college account from CRC, or from whichever California community college you are attending from within the Los Rios district, I presume, if you logged in with that, it would actually be a full access to Office.
Okay.
So log in with that account, and it should already exist. If not, do that, and that will actually allow you to save things from the internet, especially if you don't feel like installing Office on your computer, which I have no issue with. If you use it in the browser, you should still have full access to it to be able to save files, and it should be a full access to Microsoft Office. Now, your other question is therefore returning to what data do you utilize? Let me see if I can do this. Essentially, when you are looking at the lab, lab 4, open it in this one. Okay, so your data should be coming from a combination of, you should be using a combination of the area on ruler caliper. Okay, so you should take areas that you have listed. Yeah, I even take a screenshot of these real quickly, and I think I can even put these in a slide to begin with for ease of display. So you should be using as area, and then where is the weight? The mass will be coming from come on. Okay. There's that one, and then we should be using that one. So if this cooperates, then I can create 2 slides on the fly to show you the exact sources of data to use. So what you should be using are as follows. You should be utilizing, can you see my screen now?
Yes.
Okay, so for your graphs, you should be utilizing the masses that you have recorded. Let's see. Yeah, so you should be utilizing, you'll be creating a graph. Okay, this is how to explain it. You'll be creating a graph, and there'll be 4 graphs, but I'll do one example, okay? This will be a graph of, let's do, it's mass. These graphs are supposed to be, right, area versus mass. Okay, so we're gonna do area versus mass. So the graph should be, it should be, for example, ruler versus, say, analytical balance. And so you will utilize for the ruler from page 52, this set of data. This is area. These are the areas that you have calculated in millimeters squared. And then you should take, for the analytical balance, the 3 different masses that you recorded. See, it's first piece of aluminum, second piece of aluminum, third piece of aluminum. So I'll try to color coordinate these. Let's see. For example, you take this area and you take this mass, and that becomes, we'll say this is your smallest. This is your medium size. We'll do this, sorry. Smallest piece first, and that'll give you some point here. And then come along and you'll take this data point and it'll be your medium point, and that'll fall somewhere along here. And then you'll have a third point for your largest piece here, and that'll be some third data point. So you, before you create this chart, you'll create a table that is area versus mass in the actual spreadsheet, and you'll have these corresponding numbers then lined up, so on and so forth. And then you can create the chart labeled and then pull out the equation and the R squared value. that make sense at all?
Yeah,
Okay,
a bit. Yeah.
all right. I hope that helps. That is where the data should be coming from. And that should be, for example, that's just for one of the 4 that you should be generating, because there should be 4 graphs. There should be ruler versus analytical. There should be ruler versus top loading. There should be caliper versus analytical, and then caliper versus top loading. I hope that helps. Let's see here. Okay. Any other questions about this topic? Okay, if there aren't any questions about this topic, are there any other questions, briefly, that are not homework chapter 2, question 38, or questions related to the difference between orbitals and subshells? Oh my God, I'm so sorry. I did not share this with you guys, did I? Bloody hell, I went through this whole explanation and I embarrassed myself by not having it shared. Let me try sharing this if you're still here in the window. I am so sorry. This is very annoying. Oh, I am sharing it. You guys can see my PowerPoint slides?
Yes.
Okay, good. Yeah, good. Half the time it doesn't tell me that I'm sharing something today. So good. I didn't want to be doing this. If I sound like I'm explaining something to you guys and the PowerPoint slides aren't showing, please let me know, because that is a technical issue that we need to solve immediately. Anyways, anything else with relation to the graphs, the lab that is due this week? Okay, I'm going to take that as a no, and let's move on to question 2. Chapter 2, question 38. So, how many carbon atoms of mass 12 AMU are in 12 grams of carbon? So for this one, again, we need a conversion factor to go from number of carbon atoms back and forth to mass of carbon. And that's what we're looking for to begin with. We're looking for a conversion factor that allows us to do this conversion. Because ultimately, when it comes to chemistry, we want to be able to, so chemistry, of course, is at the level of particles. And when I say particles, I mean atoms, ions, molecules, etc. But the reason we use mass is because counting atoms individually is honestly pretty much impossible to do, especially in a timely fashion. So from a purely measurements practicality perspective, measuring mass, typically in grams, is way faster and more convenient and actually realistic. Because if you were to sit there and count out 6.02 times 10 to the 23rd atoms, for example, to get 16 grams of oxygen, that would take forever. I don't even have a simple word in mind for what the actual quantity of times 10 to the 23rd decimal places is. A million, of course, is 6 decimal places in front of the decimal. 23 of them, I couldn't tell you off the top of my head. Okay, so with that in mind, how do we answer this one? Well, what we do is we go carbon has an atomic number of 6 and a mass number of 12. So we do the same thing we just did. In fact, you can generally get away with the kind of quick version is the total number of protons plus neutrons in the nucleus, of course, is equal to the mass number, A. And knowing that, we can just literally say the mass of one carbon atom, therefore, is 12 times 1.67 times 10 to the minus 24 grams per subatomic particle in the nucleus. So 1.67 times 10 to the 24th grams per subatomic particle in the nucleus, because we're going to say that the mass of a proton and the mass of a neutron are roughly the same. And if we equate those, we can then do this calculation. Okay, and therefore the mass of one carbon atom becomes a little bit faster, not too much, I know, but what it does become is 12 times 1.67 times 10 to the minus 24, which therefore is 2.004 times 10 to the minus 23 grams per carbon atom. Good so far? Okay, does anyone need more time with this slide?
Where did you drop that one exponent?
Let's see. So just entering it into my calculator, 12 times 1.67 times 10 to the 24 essentially is slightly larger than 10, if you will, right? And so therefore that's where the exponent went. Does that make sense?
Okay, yeah.
Okay, cool. Okay, you guys okay if I change slides?
Yes.
Okay, so now then, the original question was, how many carbon atoms? Sorry? Pardon? I thought I heard a question. Hello? Okay, I'll keep going. How many carbon atoms of mass 12 AMU are in 12 grams of carbon? So we're taking 12 grams of carbon and converting that to a number of atoms of carbon. That's our goal. So mass of number of carbon atoms in 12 grams. So 12 grams to number of atoms now, 12 grams of carbon over 1. And then the number we have is 2.004. 2.004 times 10 to the 23rd carbon atoms. Or no, sorry. That is where I'm going to make a mistake, because that's the mass. I need to look at my conversion unit. See how it's grams per carbon atom? Because it is grams per carbon atom, grams needs to go on the bottom. So 2.004 times 10 to the minus 23 grams of carbon. And I know this because I need to get my units to cancel. And then on top, 1 carbon atom, like so. So literally what I'm going to do is divide 12 by that conversion factor I found. The double check comes from units of grams of carbon canceling. So 12 divided by, I need to look at 2.004 times 10 to the minus 23. And that gives me 5.988 times 10 to the 23 atoms of carbon. Now, these numbers are not quite the numbers that I would expect entirely, but we'll come to that in a later chapter. I can remember exactly which chapter it is. It's going to be soon. When we start talking about the mole, again, this is something that will come up when we start talking about the mole. This is all the precursor sorts of calculations you would have been doing before the unit of the mole was invented. Okay. So are there any questions about that homework question? Actually, let's see what it says in the back of the book, if it has an answer in the back of the book for this. I do not even recall off the top of my head. Answers to some problems, 2 numbers. Okay, so we got 36. 16 grams was right. So the answer we should have gotten was 6.022 times 10 to the 23rd atoms. However, the discrepancy in the answer comes from the use of this method primarily. An adjustment also would have perhaps been accounted for if I had used a slightly more accurate mass. You could find that by going 6 times 1.674 times 10 to the minus 24 grams plus 6 times 1.674 times 672, I think it is 672 times 10 to the minus 24 grams, and that actually should give you a more accurate mass per atom. 6 times plus 6 times 1.674. So, and you actually end up with a mass of 2.008 times 10 to the minus 23. And then if you take 12 and divide it by that number, still doesn't come out quite the number I'm looking for. But in general, that's the approach that would give me, that's the approach I would take. Yeah. And I just don't agree with the answer in the back of the book. Okay. How are we doing, guys?
Hi, Professor. I have a question.
Certainly.
So it's about the lab.
Okay.
So it's page 52 at the bottom where it says letter A. It asks us to calculate the area of aluminum foils and express the final answers with correct numbers of sig figs by rounding up or down. So then it says like first, second, and third, and then it says ruler, then caliper. So when we look at the above three graphs, I'm putting like the area, like the two numbers that I multiplied, I'm putting them on those lines and then changing them to millimeters.
So you're talking about the bottom of page 42?
52.
50, sorry, page 52. The bottom of page 52, express the answer with standard scientific notation. So essentially, it's just asking you to take the answers you found on page 184 in the third column and express them in the appropriate number of scientific notation with the correct number of significant figures. And part B on page 52 is a mechanism that the writer of this lab tried to create to help you guys look at number of significant figures. Yeah.
So for like the proper amount of significant figures, would I use those other sig figs from page 51?
So they should come only from columns 1 and 2. The aluminum foil. They should. So you're looking at page 51, right?
Yeah.
Okay. So when it comes to determining the number of significant figures with regard to the mass, you count all of the numbers that are significant. Yes, for the mass.
Okay, and then so for the same thing for page 52, so I'm gonna grab all of those areas that I calculated by multiplying the length and the width, correct? And I'm gonna just rewrite them, but write them in the scientific notation.
Okay, so with regard to, let's see, so page 51 is actually not really connected to page 52 as far as like number of significant figures go. You get your number of significant figures for the area from the length and the width that are adjacent to those. So if you're talking about part B on page 52, the third column, the one on the right, the column on the right hand side, needs to have you write out your full answer you get on your calculator in part B. Part C, I really don't like the way this is. My apologies. This is so weirdly alphabetized.
It's okay.
So A, calculate the area. The number of significant figures that you should have in part A beneath the tables should be based upon the number of significant figures in your measurements, which would be column on the left and center column.
Okay.
Does that make sense?
Yeah. Okay. I was confused. Okay. But then say, for example, like, okay, well, okay, no, never. I got it. I see. Yeah. Okay. So this one should be 3. This should have 4. This should be 3. This should be 4. This should be 3. And this should be 5. Okay. I got it. Thank you.
No problem. Does that answer your question?
Yeah. I have one more question. Just give me a second here. It's about the it's on page 53, part C, graphing data. Do I just what do I do for that?
So which page again? Sorry, repeat your question.
Page 53, part C. It's called graphing data.
Okay, so that is after you create your graphs. After you've created the graphs, what this should actually say is graphing data and then equation of trend line r squared value of trend line. Does that make sense?
Yeah.
Okay.
Is there like I think, did you post something about this that I would see exactly what to do on there?
Yes, I created a whole bunch of slides over the weekend that are posted under a module, and Which lab are you in?
Tuesday.
Tuesday. Okay, let me make sure, because I was doing these late at night. So if you go to modules,
Okay.
on the Canvas site, at the very bottom, there's a thing that says support material, and there is a file that says lab for measurements support material. You click on that, it
Oh,
opens something on the order of like 30 slides that I've created that
yeah, I
are
see.
all material of 49 slides now. I was at 36 last I counted. That shows you how much, yeah, anyways. So these should help, I hope. I tried to lay these out in a way that would help.
Oh, yeah. Okay. It tells me what to do.
Okay, good.
Yes, perfect. Okay.
Good,
Thank
good,
you
good.
so much. Thanks.
No problem. Please let me know if you have any other questions, and I will do my best to get back to you.
Thank you. See you
No
tomorrow.
problem. You got it. Okay. How are we doing, guys? There's never enough time in the day, of course. Now, that being said, let's see if I can answer any more questions before time runs out. Let's see here. Okay. Who do we still have? We still got 5 people here. Cool. Okay, I will ask now. Are there any other questions outside of answering the question about, I still remember this. So sorry, not subatomic, it's subshells versus orbitals. Are there any other questions? I will make sure I get to this question. Ah, boy, I apologize. It should say subshells versus orbitals. Okay, we've got 3 people left. Good deal. No questions in chat. Cool. So the best way to talk about this is to say to begin with that this is a difficult thing to conceptualize. There's a couple of different ways to think about it. You can think about the primary shell, which is sometimes also called the primary energy level. They mean the same thing. And what that means is you're talking about now basically an area of space where electrons all have roughly, approximately the same energy. Okay, the primary shell. From there, we get to the next thing. I'm going to move a little fast here just because I'm trying to make sure I answer this. The subshell essentially is a region of space where electrons all do have the same energy. So it's no longer approximately the same. It's now they do have the same energy. Okay. But the electrons don't actually exist specifically in the subshell. The subshell is essentially a energy description, and the orbitals within the subshell are the actual region of space occupied by, at most, a pair of electrons. This goes back to my analogy about how these 3 quantum numbers give you the address, and the 4th one gives you the name of the electron. That's how we go. N is the city. We then go L is the street, and then we go M sub L is the house occupied by the electrons, and then M sub S is the name of the electron inside the house. And these four things are: N is the primary shell, L is the subshell, which is, of course, your S, P, D, and F. The subshell does also tell you one other thing. The subshell also tells you the orbital shape, and the house, M sub L, the house is the actual orbital, and these are the spin. Okay. That's kind of the fastest review of that material I can do without trying to be like ridiculously fast about it. Does that help clarify at all?
Yes. So, but the orbitals, the actual orbitals, they're the ones that have the either the positive or the arrows going up and down is the spin or the charge?
So yeah, that's a very good question. Every electron has the same charge, which is negative. The arrows up and down, the spin of plus a half or minus a half are the arrows. And spin plus a half is up, spin minus a half is down, and usually we actually use little half arrows for these. Traditionally, we do this with a little half arrow to kind of, well, for a number of reasons, but we'll just say, to make the easiest explanation of why, is that it is to indicate that half spin, if you will.
Right.
Yeah.
Well, like if you see, like I wrote, I guess that's probably backwards for you, right?
Oh no, I can see it right the correct direction. Thankfully, Zoom does actually correct it.
All right.
Yeah.
So so I wrote down this from the book, and then I also wrote down this is
Yes, exactly. Yes, that is how you would fill the orbitals within a subshell. And now what I can do is two things in response to that. So what you just provided me with was the first one was, remind me, it was the type of subshell, right?
right
And then you said the number of electrons
capacity.
in it, the capacity, yeah. And one other thing we can is the number of orbitals in a subshell is another thing we can add there. And so the subshell S, P, D, and F. And we can say here that the number of electron capacity of S, so number
Hard
of
to hear you.
orbitals. I don't know who's talking. Oh, Cynthia. Cynthia, I think, unfortunately, is currently broadcasting. There we go. She went quiet. Okay. So the number of, let's start by saying for an S, the number of orbitals within an S subshell is 1 orbital. And from that means there's only going to be 2 electrons total in that subshell, because there's only 1 house on that S street, or there's only 1 orbital within that S subshell. So it actually is because there's only 1 orbital within that S subshell that there's only 2 total electrons in that subshell. Within the P subshell, you have a possibility of total of 3 orbitals. So 3 orbitals within an S subshell. And because of that, because each orbital can hold a maximum of 2 electrons, it's 2 times 3 is 6 total electron capacity for a subshell. And let's see here, trying to mix up the colors, but whatever, it's not that vital. D has a possibility of 5 orbitals within that subshell. And because of that, 2 times 5, because there's a total of 2 electrons per orbital, means that you can get a maximum of 10 electrons per subshell. And finally, F, there's a possibility of a total of 7 orbitals per subshell. So therefore, there's a total possibility of 14 electrons per subshell. And that's because there's a pair of electrons that exist within an orbital. And then there's a maximum number of orbitals that can exist within a specific type of subshell.
That's crazy.
I know, that's why I try to, trying to picture this in your head with regard to the abstract concepts of subshell and electrons and orbitals and primary shell is very confusing. And so therefore, the analogy is the best option we have.
Yeah. All right. I think you gotta, I'm sorry for keeping you over your time, but
No problem. No problem. Yeah, no, I'm gonna get going. I hope this was helpful. I'm sorry I don't have more time for questions. I'm sorry I don't have more time for you guys.
Sounds good.
Yeah.
All right.
Have a
I'll
good
see you
night.
on Thursday.
You got it. Have a good night.
All right, peace.
Bye.